Hello, students. Welcome back. In our last sessions, we handled integrals that were quite direct. We could spot them because they matched some known derivatives. That method is called inspection. But what happens when the function is not so friendly? What if it doesn't look like the derivative of anything you've memorized? That's when we need systematic methods of integration. In class 12, we focus on three major ones: integration by substitution, integration using partial fractions, and integration by parts. These three cover most of the difficult integrals you'll see in exams. Let's begin with the substitution method. The idea is simple: change the variable into something easier. Suppose we have an integral f of x dx. If we let x equal g of t, then dx becomes g dash of t dt. The integral transforms into f of g of t multiplied by g dash of t dt. This new variable often turns a difficult integral into a standard one. Think of it as changing the viewpoint to make the problem simpler. Let's see substitution in action. We want to evaluate 2x cos of x squared dx. Step 1. Let t equal x squared. Then dt equals 2x dx. Step 2. The integral becomes cos t dt. Step 3. That's a standard form. The integral is sin t plus c. Step 4. Replace t back with x squared. Final result: sin of x squared plus c. Notice how substitution turned a tricky integral into a very familiar one. Next up is partial fractions. This works for rational functions. That means a fraction where numerator and denominator are polynomials. The idea is to break down a complicated fraction into a sum of simpler fractions, each of which is easy to integrate. For example, take 1 over x squared minus 1 dx. The denominator factors as x minus 1, x plus 1. Using partial fractions, we can write 1 over x squared minus 1 equals 1/2 into bracket 1 over x minus 1 minus 1 over x plus 1 bracket close. Now, integrating becomes a piece of cake, just logarithms. Let's work through that example step by step. We start with 1 over x squared minus 1 dx. Step 1. Write 1 over x squared minus 1 as 1/2 into 1 over x minus 1 minus 1 over x plus 1. Step 2. Now split the integral 1/2 1 over x minus 1 dx minus 1/2 1 over x plus 1 dx. Step 3. These are standard forms. We get 1/2 log modulus x minus 1 minus 1/2 log modulus x plus 1 plus c. Final answer: 1/2 log modulus of x minus 1 over x plus 1 plus c. Now for integration by parts, a very powerful method when we have a product of two functions. The formula is u v dx equals u multiplied by v dx minus derivative of u multiplied by v dx, all integrated again. Choosing which function is u and which is v is critical. For that, we use the Liet rule. It stands for logarithmic, inverse trig, algebraic, trigonometric, and exponential. The one that comes earlier in this order is chosen as u. This choice can make or break your solution. Let's solve an example. The integral of x into e to the power x with respect to x. Step 1. Choose u equal to x so that du equals dx. Then let v equal e to the power x. Because the integral of e to the power x dx is just e to the power x. Step 2. Apply the formula for integration by parts. Integral of x e to the power x dx equals u times the integral of v dx minus the integral of du multiplied by the integral of v dx. That means x multiplied by e to the power x minus the integral of e to the power x dx. Step 3. Simplify. That becomes x e to the power x minus e to the power x plus c. So, The final result is open bracket x minus 1 close bracket multiplied by e to the power x plus the constant c. Notice how the by-parts method handled the product smoothly and the choice of u equal to x made the problem straightforward. Let's wrap this up. Inspection is quick but very limited. To go further, we master 3 methods. First, substitution, change variables to simplify. Second, partial fractions, break rational functions into smaller pieces. Third, integration by parts, handle products using the Lie rule. Together, these methods cover most of the integrals you'll face in Class 12 and competitive exams. And that's the power of methods of integration. In the next video, we'll dive deeper into solving standard integrals using these techniques. Stay tuned.